Hello students, my name is Ayela Gabri. I am physics teacher. This is grade 12 physics lesson unit 3 fluid mechanics. Lesson 5 Pascal principle, Archimedes principle and fluid flow. After the completion of this lesson, you will be able to explain how Pascal's principle is used in hydraulic press machine, solve problems using Pascal principle and Archimedes principle, derive equations of continuity from flow rate, use equations of continuity to solve problems. Before we are going to deal today's lesson, let's revise some pointers about fluid mechanics. Fluid mechanics is the study of fluid, that means liquid and gas, in motion and at rest. If it is in motion, we call that is fluid dynamics, and if it is at rest, we call that is fluid statics. Fluid is a name, any substance. Fluid is any substance that can flow and changes the shape of the volume that it occupies. We use the term fluid for both gas and liquids. The key difference between them is that a liquid has cohesion while gas does not. Fluid statics is the study of fluid at rest in equilibrium situation. We will see this in the next section. An important property of any material, fluid or solid, is its density, defined as the mass per unit volume. Fluid at rest, the shear stress is 0 and the only exerting force is the normal force, and it is called pressure. Pressure is defined as the normal force exerted by a fluid or a solid per unit area. If F is the magnitude of the force exerted on the fluid or a solid at a perpendicular point, and A is the surface area at which this force is applied, the pressure P is given as P is equals to force over area. This is the expression for calculating the pressure of a given force at a given area. Now let's start today's lesson first about Pascal principle. Pascal principle is one application of fluid statics that can have applied in when the fluid is at rest. Pascal's principle, also sometimes known as Pascal's law, states that when a change in a pressure is applied to an enclosed fluid, it is transmitted and diminished to all portion of the fluid and to the wall of the container. This is what we call the Pascal's principle. The pressure spread out uniformly due to increased molecular collision regardless of where it is applied. Pascal's principle is applied in hydraulic lift or hydraulic press, hydraulic brake, that means the car brake, and hydraulic pumps. We use the Pascal principle for all these systems. One of the technical applications of Pascal's principle is hydraulic press. The hydraulic lift or hydraulic press illustrates Pascal principle. The hydraulic lift is a force multiplier device which multiply by a factor equals to the ratio of the area of the two pistons, which means if we apply some amount of force, this hydraulic lift multiplies these forces. For example, if give a 1 Newton force, the hydraulic press may output that is 2 Newton force, which means force multiplier device means this. A piston which small cross-sectional area A1 exerts a force F1 on the surface of a liquid such as oil, then the applied pressure P is equals to F1 over A1 is transmitted through the connecting pipe to a large piston of area 2. So this video can help to understand what hydraulic press is. Let's see, if F1 is applied here and it will have lower a distance di, and in the other side the object will move up. That means the change in the pressure of this piston and the change in the pressure of this piston is equal, not the pressure, the change in pressure. The pressure and the change in pressure are not the same. The pressure may not be the same, but the change in pressure, the pressure that change in this piston or a smaller piston is equals to the change in pressure in the larger piston. You can look here, there is F1. So this hydraulic press can multiply this force in the second piston. It can lift very heavy objects by applying a small amount of force. This illustrates that how Pascal principle is applied in real life of our day-to-day activity. So let's practice examples concerning this Pascal principle. What would be the ratio of the diameter of the smaller piston to the larger piston, small d over capital D of a hydraulic system, so that when a force of 100 Newton is applied at a smaller piston, the force that is produced by the larger piston would be 10,000 Newton. Let's do the exercise. Solution. Given that means area of force of a small piston is equals to 100 Newton and force of larger piston is equals to 10,000 Newton. Then the required is the diameter of the smaller piston to the diameter of the larger piston. Or okay. 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 Sorry. Okay, solution given. We have a given that is F of a smaller piston is equals to 100 Newton and the force in larger piston is equals to 10,000 Newton, and the required is the ratio of the diameter of the smaller piston to the diameter of the larger piston is equals to how much? So we can apply the Pascal principle to solve this problem. Pascal principle said that the pressure change, which means F small over area of small is equals to F at the larger piston over the area of larger piston. Here we have think that since it is a cylinder, therefore the cross-sectional area is pi r square, which means pi d square over 4, because radius is half of the diameter. Then this means F1 over area means pi small d square over 2 is equals to force of large over pi times d capital D over 2 square. This gives us F1 over pi d small d square over 4 is equals to F large over pi capital D square over 4. We can simplify, by the way, 4. Then we get that F small over pi small d small d square is equals to f of large over pi capital D square. Again, we can simplify this pi. Then we get that the algebraic solution fs over d square is equals to fl over capital D square. Now we can take the ratio. That means f small over fl is equal, f large is equals to d small square over d capital means the larger piston square. Now we can substitute the value. If we substitute the value, d small square over d capital square is equals to the force on the smaller piston is 100 Newton and the force on the larger piston is 10,000 Newton. After simplification, this becomes smaller d square over capital D square is equals to 1 over 100. Then finally, we can take the square root of both sides. If we take the square root of both sides, we can get small d over capital D is equals to 1 over 10. Then the ratio small d to capital D is equals to 1 to 10. This is how we can apply the Pascal's principle in solving problems. So let's see next the Archimedes principle. Archimedes principle states that when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equals to the weight of the fluid displaced by the body, or the buoyant force on an object equals to the weight of the fluid that it displaced. This is what we call Archimedes principle. The upward force exerted by a liquid on any immersed object is called a buoyant force. Buoyant force is greater upward force at the bottom of an object than the downward force of the object at the top of a fluid, at the top of the object on a fluid. Buoyant force is greater upward force at the bottom of an object than the downward force on the top of the object in a fluid. Archimedes principle can be expressed in mathematical form. The first one, in equation form, Archimedes principle is given as the buoyant force Fb is equals to the weight of the displaced fluid. When an object partially or wholly immersed in a fluid, there is a fluid that is displaced due to the insertion of this object. That force is equals to the weight of the displaced fluid. Here weight means mg, and from this mass is also equals to density times volume. Using this idea, we can substitute this one. This density is density of the fluid times the volume of the displaced fluid times the gravitational acceleration will give the buoyant force, which pushes the immersed object upward. Where this rho fluid means that is the density of the fluid, and v displaced means the volume of the displaced fluid, and g is the gravitational acceleration. When an object immersed so when this object is immersed in the fluid, there is a displaced fluid, mass of displaced fluid. So the weight of this displaced fluid and the buoyant force that pushes the object upward is equal. Look at this one. When the object immersed in this fluid, there is a displaced fluid here. So the weight of this displaced fluid is equals to with the weight of the buoyant force of the object that pushes upward. So this is what we call Archimedes' principle. Buoyant force is equals to the mass of the displaced fluid times the gravitational acceleration. So this is how the Archimedes' principle is applied in real life. We have considered Archimedes' principle for two cases: when an object is totally submerged in a fluid and when an object is partially submerged in a fluid. Let's see the first one, when an object is totally submerged in a fluid. When an object is totally submerged in a fluid of density, rho density of fluid, the volume V of displaced fluid of the displaced fluid is equals to the volume of the object V object. So the magnitude of the upward force, buoyant force, that means, is equals to, then the displaced fluid, the weight of the displaced fluid for this case is equals to that of the buoyant force. This is equals to F of fluid is equals to V of object. Because if the object is totally immersed in a fluid, the volume of the object and the volume of the displaced fluid will be equal. This is only when the object is totally submerged in the fluid. So from this, we can have that if an object is totally submerged in a fluid, there is also a gravitational force that pushes or that acts downward. Then the net force for this case, F buoyant, is upward force, and Fg or gravitational force is downward. Then when we take, that means if this one is taken as an object that is submerged in a fluid, there is, if the object has mass m and volume v of object, and its weight is equals to Fg is equals to mg. That means density of the object times the gravitational acceleration times the volume of the object. Then the net force on the object will be buoyant force minus the gravitational force, because there is an upward force Fb, buoyant force, that means there is a downward force, the gravitational force, that is Fg. So if we sum up these two forces, we get that Fb minus Fg. Since the gravitational force is downward, we take negative. So Fb minus Fg is equals to the density of the fluid minus the density of the object times g times the volume of the object. From this equation, we can have the following conclusions. If the density of the object is less than, the density of the object is less than the density of the fluid, an object accelerates upward, which means the upward force greater than in this case. And the next case, if the density of the object is greater than density of the fluid, the object will sink. If the density of the submerged object equals to the density of the fluid, the net force on the object becomes 0, and the object remains in equilibrium. It can be anywhere inside the fluid. It cannot move upward, downward. If once stationary, it can have a stationary position in everywhere inside the fluid. Therefore, the direction of motion of an object submerged in a fluid is determined only by the densities of the object and the fluid. The next case concerning what Archimedes' principle is that when an object is float, which means it does not sink. In this case, the upward buoyant force is balanced by the downward gravitational force acting on the object. if the volume of displaced fluid is, if the volume V is displaced by an object, that means the volume of the object, that the part beneath the surface of the fluid, the buoyant force has the magnitude of F is equals to density of fluid, volume of displaced fluid times the gravitational acceleration. This V displaced is equals to the part of the object below the surface of the fluid, and Fg, a gravitational force, is equals to the mass of the object times gravitational acceleration times the volume of the object. In this case, the floating, in the case of floating, density of object is less than density of the fluid. The upward buoyant force is balanced by the downward gravitational force acting on the object. Then we can have the following. If an object is float, the upward buoyant force balances the downward gravitational force. We can substitute the expression for each. For buoyant force, we have this one. Density of fluid times the volume of the fluid times the gravitational acceleration is equals to the density of the object times the gravitational acceleration times the volume of the object. The gravitational acceleration in both sides will be cancelled or simplified. So if we take the ratios, we get that the volume of displaced fluid over the volume of the object is equals to the density of the object over the density of the fluid. This gives us how much parts of the object is below the fluid in the ratio of the volume of the object outside the fluid. Very important question. So let's see an example. An iceberg of density 917 kg per meter cube is floating in a water of density 1000 kg per meter cube. What is the percentage of the volume of ice cube outside the water? Let's do this one. We can apply for calculating such types of problem using Archimedes principle. Solution. We have a given here, a given that is density of object is equals to 917 kilogram per meter cube, and density of fluid is equals to 1000 kilogram per meter cube. This is water. What is the percentage of the iceberg outside the water? So the required is, so what is the part of the volume V outside in percentage. So to find this problem, solve this problem, we can use the ratio or the Archimedes principle. That is the volume of displaced fluid, which is a part of the volume of the object below the surface of the fluid, over the volume of the object is equals to the density of the object over the density of the fluid. Then we have asked to calculate this one. After we get this one, we can express in percent. Then we have to subtract from 100% to get the part of the iceberg outside the fluid. So this is equals to the density of the object is 917 kilogram per meter cube over that of 100 kilogram per meter cube for that of the fluid. Then this becomes 0.917. In percent, in percent, this is equals to 91.7%. Students, don't confuse. This is the part of the iceberg below the surface of the fluid. Now, to find the part of the iceberg outside the fluid, we have to subtract this one from 100%. So this is the outside part in percent is equals to 100% minus 91.7%. Then I think this becomes 8.3%. 8.3%. This is why in boats or submarine materials it can have a problem, because it cannot, all parts of the iceberg does not observe it. Most parts is inside, so when the boat is traveling or moving on the water, it will have a danger for the case of these such types of problems. So this is very important to see or to calculate how much parts of the iceberg outside the fluid. So the last topic that we'll see today is that fluid flow. Fluid flow is caused by the difference in pressure. Fluid rate can have used to express how much amount of volume is flow at a given time. Then fluid rate is the volume of the liquid flowing past a given point per unit time. Flow rate is given by Q, which means flow rate, is equals to V over T. V is the volume. Don't confuse. It is not a velocity. It is a volume. Volume, and T is the time elapsed or the time taken for flowing a given fluid. So the SI unit of flow rate is meter cube per second, because the unit of the volume is meter cube and the unit of time is second. So the unit of flow rate is meter cube per second. Okay, concerning the flow rate, there is equation of continuity. Equation of continuity states that the mass flow rate of fluid flowing into a system is equals to the mass flow rate of fluid leaving the system. This is given by, in equation form, the Q or flow rate in the first one is equals to the flow rate in the second pipe. The flow rate in the second pipe on a second system. This can be given by, because Q is equals to V over T. V over T. V is volume in this case, which implies that we can find that A1 times V1 for the case is equals to, V is equals to the flow rate Q times T. Q times T. And in this case, by the way, V means, the volume means area times length over T. This L over T, or distance over T, means the velocity. In this equation, V is not the volume, it is the velocity. It derives from this equation. So that means Q rate also can be given by area times the velocity. This is velocity, not volume. Velocity. So this equation of continuity is given by area of the first system times the volume of the fluid in the velocity. Area of the first system times the velocity of the first system is equals to the area of second system times the velocity or the speed of the second system, is equation of continuity. So this is the equation of continuity, and it is valid only for incompressible fluid. If the fluid is compressible, we do not apply this equation of continuity, because when the fluid is compressible, there is a decrease in volume. So for that case, we do not use this expression. this equation of continuity used to relate the cross-sectional area A and the average speed V of the fluid in different parts of rigid vessels carrying an incompressible fluid. The mass of fluid doesn't change as it flows. The speed is high where the tube is constricted or narrowed, and low where the tube has larger diameter or larger area. Area and the speed for this case is inversely proportional. So let's do an example concerning this equation of continuity. Water flows through a pipe whose cross-sectional area is 25 centimeter square into another pipe whose cross-sectional area is 5 centimeter square. Both pipes are horizontal. If the velocity of the water in the larger piston pipe is 6 meters per second, what is the velocity in the smaller pipe? So let's do the solution. Solution. We have given A1 is equals to 25 centimeter square, and area 2 is equals to 5 centimeter square, and V1 that means the velocity in the larger piston is equals to 6 meters per second. The required is V2. So we can apply the equation of continuity, that is area 1 times velocity 1 is equals to area 2 times velocity 2. So the required is velocity 2, it is V2 is equals to area 1 V1 over area 2. We can substitute the values because we do not expect to change the unit of the area into meter square, because it is the ratio. Simply they will be cancelled out because the conversion factor is multiplication. So this is equals to area 1 is 25 centimeter square times V1 is 6 meter per second over area 2 is 5 centimeter square. The unit will be cancelled as I have told you previously. So 25 divided by 5 is 5. 5 times 6 is equals to 30 meter per second. Students, have you seen if the area decrease, the velocity increase? This is what we understand from the equation of continuity. Okay, this is the solution for this example. Then, student, the next one is exercises that you practice in your home and compare your answers with the given answer key here. To practice the exercises, there are 4 questions. Practice in your home. So let's summarize what we have discussed today. Pascal principle states that when a change in pressure is applied to an enclosed fluid, it is transmitted and diminished to all portion of the fluid and the wall of this container. And Archimedes principle states that when an object is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equals to the weight of the fluid displaced by the object. And the last one is equation of continuity. Equation of continuity states that the mass flow rate of fluid flowing into a pipe is equals to the mass flow rate of a fluid leaving the system. This is all about for today. Students, don't forget practicing the exercise and compare your answer or check your answer with the answer key. Thank you very much. Have a nice study for you.